There's a big difference between sequences and series. See, the sequence is just a list of numbers. So we would have a to the n equals a1, comma a2, and then comma, up to a to the n. Now, there's two ways that we can describe a sequence, a list of numbers. The first one would be an explicit formula. So a to the n equals 2 to the n. This is explicit. And that would be sort of like, 2 to the 1 power, and then 2 to the second power, which is 4, and then 2 to the third power, which would be 8. So you sort of have this list of numbers here. Or you could also describe this recurrence relation between them. So something like a equals 2a to the n minus 1. And this is kind of like, this is the previous one times 2 will get you the next one. It's kind of this funny way to say that, but this is the recurrence relations. Recurrence relation. All right. And so then there's going to be like two types of ways that you can get this way. You can either have an arithmetic sequence, and that's going to be just like a to the n would be, a to the n minus 1 plus or minus some sort of slope. So it would be just like, kind of like a slope in a line. You would say, hey, you could add 2 and then add 2 and then add 2, and or you would have a geometric one, which is actually what 2 to the n is, geometric, because a to the n is actually equal to r times a to the n minus 1 over here. And this is the previous one times 2. Instead of plus 2, it's actually times 2 in this situation. So it's the previous one times 2. So if we were to take the limit of one of these sequences, the limit of a to the n as n goes to infinity, we would essentially get the last term, the very last term, L, of the sequence. It's the infinite term, it's the last term. Now we would say, okay, it will diverge if that last term is either infinity or dne, because it doesn't exist, or we would say, okay, well, it converges to a specific number if L exists. So we're kind of going to be taking a look at either whether a sequence will diverge or converge. But keep in mind that sequence convergence is equal to the last term of a sequence. And series divergence is going to be the next concept in the next portion, but it's different. So sequence divergence and sequence convergence and series divergence and series convergence. Sequences and series are different, so they're both going to have different types of actions. All right, so when we talk about sequence convergence, it's the last term. When we talk about series convergence, that's something else. You may have also heard of the squeeze theorem, and it will apply to the sequences as well. And it's basically this. So if we have the squeeze theorem, which says if you have a to the n, that's one sequence on that side, it's a smaller sequence, and you got some sequence sort of sandwiched in the middle of one that's much bigger here, c to the n on this side. So you have these three sequences. This side is much bigger, that side is a little smaller. But if you can prove that the limit of a to the n, as L goes to infinity and stuff, is L, well, then the limit of c to the n is also the same. If you can prove that these two limits are the same, a to the n and c to the n, then obviously the one in the middle, the limit of b to the n, is equal to L as well. It's kind of confusing, but you can just sort of see, if this goes to a specific number and that thing goes to a specific number, then that must also be that same number because it's sandwiched right in between. They go to the same spot. So the series is actually adding all the numbers up. This is the series. It's almost as if it were an integral. It's actually the sum of a sequence. It's almost like an integral. But let's say we have a s, this is the sum, and we'll make this little sigma notation. We're starting at n equals 1, going all the way to infinity in this particular case, of this sequence a to the n, just means that we're going a1 plus a2 plus a to the n, which would be infinity in this particular case. Starting at 1 with n equals 1, going to infinity in the n over there. So this is how we could sort of add up the sequence. We can also say it goes to a very specific number, calling it a partial sum. This is a partial sum, and that's just going to be signified as n equals 1 to the k, and this would be ak equals a1 plus a2 plus a to the k. Okay, now remember that series convergence is different from sequence convergence. So if we have series convergence, that's really going to be meaning that you're finding a real area after you add up all these numbers. So like, if you don't get a real area, then it's either an infinite area or the area doesn't exist. If you add up all these numbers and then just you don't get an answer, then it'll diverge. But if you do get a real area, then it'll converge. Let's examine the geometric series, which we get this from the geometric sequence over here, but it's written as n equals 1 to infinity over here, a1. This is the first a. If we were to plug in n equals 1 over here, then it will just give us a1, and then that we'll want to multiply that by the recurrence relation that we had with our r to the n minus 1, so that way we could start at 1, and that would be r to the 0 if you have that. So anyway, so this will work out for geometric sequences if you're trying to get the formula for one of those. And then this, if you're trying to figure out the sum of the geometric sequence, that sum right there from 1 to infinity is just a to the a1, this is a1, and then over 1 minus r. So that'll help you sum one of these geometric series up. You can get the answer for a geometric series. Of course, you can also get the partial sum like we were talking before, the SK version, which would be a1 and then times 1 minus r to the k up here divided by 1 minus r. Okay, and this will just get you the partial. If you're not going to infinity, then this is why over here, if that was infinity, then we'll have two specific situations over here. It will converge if the absolute value of r is less than 1, or it will diverge if absolute value of r is greater than or equal to 1, because if we have r being less than 1, this is a fraction here, and we send the fraction to infinity, that'll just cancel out, and then we'll just get this answer right here. So if you get a real sum, it will converge to this specific number when that goes to infinity, but it'll just diverge if that's greater than 1. If it's greater than 1, then this will just be infinity, and then this whole thing, this will just diverge, including this. So if r is greater than or equal to 1, that was going to be the recurrence relation over here, that one. If r is greater than or equal to 1, then this will just turn into an infinite answer, and that's how we get the divergence situation when we look at this geometric series. There's a really cool trick we can use for series that are written in the right way. It's called telescoping. I'll try to explain this in English. It's called, basically, we could say the first term of the sequence on the left, minus the last term on the right. All right, and so if we had a series written as n equals 1 to infinity, 1 over n plus 1, if we were going to try to add that up, we actually have to rewrite this like this with partial fractions. We could say 1 over n minus 1 over n plus 1. So that's pretty cool. It separates it out into two different fractions like that. Sometimes this will work out, sometimes it doesn't. And we want to do the first term on the left minus the last term on the right. That's going to be written as sk is equal to a1 minus b to the k plus 1. All right, so this is the first term on the left minus the last term on the right. And it's called telescoping. Kind of a cool trick. Now that we know the difference between the sequence convergence, which is saying the last term of a sequence, and let's imagine this line being a sequence, it's going to be just like coordinates along this line. It's not going to be the actual line, just some coordinates, right? You'd say the last coordinate on this. That is what we're talking about, sequence convergence. And over here, the series convergence is be the real area. So if we added up the area under this curve, then we would get a real number. So those two things are completely different concepts, but they're related to each other in this way. So we can say, hey, let's look at the divergence test. If the limit as n goes to infinity of the sequence, which is a to the n over here, if the last number over here is not 0, this line has to hit 0 in order for this area to be real, because if this thing is not 0 and it was up here at a 1 or some sort of weird other negative number or something, this area won't be a real area, and you'll get like an infinite area or some area that doesn't exist. So the last number of that sequence has to be 0 in order for this to form a real area that's actually a box. Otherwise it'll be an open box that won't have a closed, there's like going to be a hole in the box, and that's not a real area. So it's very important that this number hits 0, and that's the divergence test. So if it does not equal 0, that limit, then we basically just have to stop. We don't really care too much. The sequence diverges, the series diverges, and everything diverges. So that's pretty cool. Rewritten here, if the sequence must converge to 0, otherwise the series will diverge. So that's just written in English what the divergence test means. Now I drew some red boxes here on this graph to show you the difference between a function, which is f of x, this line right here, we'll call that f of x, and then this right here is the sequence, or really the series if you're adding them all up. The problem with the series is that it's not continuous, it's a block, and so that's why you have these rectangles here to sort of describe the sequence or the series area. So if you were to add up all these boxes, you could see the area is actually going to be a little bigger than the size of the area of the function, right? That area under the curve of the function is a little bit smaller than the area of that one. So with that in mind, we can actually start using the integral test here, the integral test. Because if we can prove that the integral of that line, f of x, actually gives us a real area, then we know that this sequence will also converge. But if we have shown that we get the integral being equal to infinity or dne, then that means that we didn't get an actual answer for the integral under this thing, and so obviously it's going to be the same thing for the sequence and the series. That's also going to diverge if we get the integral right there. So that is called the integral test. It's kind of cool that we can just kind of use the integral to distinguish whether the series will diverge or not. The only problem with the integral test is it can sometimes feel like brute forcing, and that's not really all that much fun. So it'd be cool if we had a way that we can just immediately tell if a series will converge or diverge. And we have these things called p-series, which will really help us out. It's sort of something like given in the form of n equals 1 to infinity of 1 over n to the power of p. So it'll be something like 1 over n or 1 over n squared, 1 over n to the third, whatever. We've already done the integrals, and we've calculated ahead of time that, that if p is greater than 1, then this will converge. So if you have 1 over n squared, 1 over n to the third, 1 over n to the fourth, those will converge. But if you have the p-value of being less than or equal to 1, then it will diverge. So that would be 1 over n, or anything less than p is less than 1, something like that. And one more important concept here, if ever necessary, if we go to infinity, we add up 1 over n squared. They've already figured out, for some reason, that this is equal to pi squared over 6. Just in case you ever need to know that. Another good way to figure out if your series converges or not is to use a direct comparison test. So let's say your series was just a little bit smaller than one of the p-series. So you can prove that, for example, 1 over n squared plus 1, well, that's going to be smaller than 1 over n squared, right? So you can prove quite easily that n equals 1 to infinity, this side converges, and therefore the left side will converge as well, due to the direct comparison, because it's a smaller sequence, and so if the bigger sequence will converge, the smaller sequence will converge. It's pretty simple. And we can also say the opposite as well. So let's say your series was just a little bit bigger than that p-series that's 1 over n, right? 1 over n. and you have 1 over n minus 1, for example, well, you know that that's bigger than that one. So you can prove through direct comparison that if this one were to diverge the smaller one, this is the smaller one, it diverges, then obviously the bigger sequence will diverge as well. And that clearly just makes a lot of sense. Now, the direct comparison test will work very well if you can simplify something down, to a p-series. You know, you kind of remember, you're sort of canceling things out, and you're saying, hey, that kind of looks like that p-series, right? And then you're like, okay, well, let me try to compare it to that, right? But let's say if it doesn't work out properly, and you can't figure out one of these direct comparisons, then you can use the limit comparison, in which case you just divide them. So you're going to say that the limit of n goes to infinity, you're going to take the series you got, and you're going to divide it by that p-series that you want to compare it to, and then you're going to need to get a real number here that's not 0, it's not negative, this has to be positive, everything all has to be positive, of course, both of these have to be positive. It's kind of the thing about most of these things. But if you can prove that, then you can shift bn over to the other side, and you can say that the sum here of a to the n is just about equal to k times the sum of b to the n. And so therefore, those two things that you were comparing, they're going to experience the same behavior. And so if you can prove that particular number exists, then this will work out for you. And we also have the alternating series test. Alternating series. This is going to be if something is like plus minus, it's going to be alternating between those signs. And we can sort of represent this by -1 to the power of n, or it might be n plus 1 right there, but that would be an. And usually these things are just going to have to be, a to the n is going to be positive, mono, and decreasing. This is very important for most of these things. Things usually have to be positive. You see, these sequences, these series have to be positive. They got to be monotone, decreasing, so that it looks like this. If it's in other shapes, then obviously these things don't really work. But if you can show that, and you can show that the limit of a to the n is also equal to 0, then well, alternate series will converge. Yeah, so if you got the plus and minus, and it's doing that, and the limit, the last one of that sequence, is equal to 0, then that's going to be equal to it's gonna converge. So it's cool about the alternate series. We could also use the Dirichlet test. This is very similar to the alternating series. So we could say that it kind of also works if a function is bounded. All right, so here's bn. That's just a bounded function, like a trigonometric function. So bn is bounded. It will work the same way because we have something, instead of being -1 plus and minus, this little thing is bounded right over here. That would be something like sine or cosine. Sine or cosine, that's just waving like that. It's the same thing as going plus or minus, right? But our an still has to be positive, monotone, decreasing in the shape of that. That's kind of going to be a very theme that goes across all these, of course. Along with the alternating series comes the absolute convergence and the conditional convergence. So absolute convergence is when you have the absolute value of the series converges. So you've got this alternating series that might be plus or minus. You take the absolute value, and that converges. Or you could, pretty much any series. You take the absolute value, it converges. You've got absolute convergence. But on the other hand, you might have conditional convergence, which means that, let's say the absolute value will not converge and the absolute value diverges, but the regular one, the regular sequence converges. Oh yeah, so you could take 1 over n, but put that in the alternating series by giving it a -1 that, and you put 1 over n over there. Well, that will converge. But the problem is, if you take the absolute value of that and you put 1 over n, 1 over n does not converge. But if you give it the plus or minus, it'll converge. So 1 over n will actually work out for this particular situation. With the plus or minus up here, if you get the -1, you put n over there, that will converge. But on the other hand, if you go over here, n equals 1 to infinity, the absolute value here, if you put the absolute value around that, you'll just get 1 over n over here. And, well, we can see that that's not going to converge, that's going to diverge. Now for this next test, we're going to point out some very important things. N factorial is equal to 2 pi n. This is approximately equal to that. This is a Stirling's approximation, n over e to the power of n. This is Stirling's approximation. And we also have n plus 1 factorial is going to be equal to, and this is actually equal to, n plus 1 times n factorial. So these two things are going to help us understand why the ratio test might be important for some of these particular things. If you have something that has n plus 1 factorial might happen to have that. You can sort of manipulate that around and make that work out for you. But it could also work if you just happen to have like you know, some really weird things. You don't know how to set them up. You could just try the ratio test. But anyway, let's just think what that means. So you get the n goes to infinity limit here, but you're gonna plug in n plus 1 into your n's, and then you're also gonna use the regular one on the bottom. So yeah, so instead of having you're going to compare the n plus 1 version of your series to the n version of your series, and see what kind of number you get out of that. It's going to be very similar to what will happen over in the geometric series. So if r absolute value is less than 1, it's going to converge, and if r is greater than or equal to 1, it's going to diverge. This is just because same reason that we had for the geometric series. We can also use those same principles of these r converging and diverging if we use the root test. This is, for example, if you have something to the power of n, right? Like a thing to the power of n, a sequence to the power of n, and you can get rid of it by dividing it out. So if you get the sequence to the power of n, just divide it out from the top, and then figure out what number you get from that. If you can send that to infinity and actually get a real limit, then you can say, hey, if that r converges and that r diverges, you got some numbers that you could set up here for that. The final test that we have is called the Cauchy Condensation. Cauchy Condensation. It's quite an interesting one. Again, everything has to be positive, and then mono decreasing. But let's say we had n equals 1 goes to infinity. I'm going to rewrite this as f of x instead of being like an. I'm going to do that because this is basically like you're gonna be plugging in 2 to the n into your n values. So it's kind of like if you had your sequence of in n's, then plug in 2 to the n. Okay, so I'm just kind of say that the an is kind of like f of x, and that x is equal to 2 to the n. So plug in x values into the f of x over there, and kind of pretend like f of x is your thing. So you're going to rewrite this as 2 to the n times, then just plug in that function that you had with all your n values plugged in as 2 to the n. You got your 2 to the n, and then your f of 2 to the n here. Cauchy condensation will work pretty well if you've got like ln of 2 to the n equals n ln of 2. Remember that this rule right here, you can shift the n over here, and you get n ln of 2, something like that. This will work well for Cauchy's condensation. So these are all of the different techniques and tests that we can use. Not all of them, even there's more, but many of these tests that we can use to just figure out series and sequence convergence and divergence. These are quite powerful tests. Now, hopefully you enjoyed this video. If you like this, just subscribe. This is some crazy stuff.